Schönen guten Tag, liebe Teilnehmerinnen und Teilnehmer. Ich freue mich sehr, Sie zu unserer nächsten Auflage unseres Kolloquiums aus dem Studiendekanat Elektrotechnik, Informatik und Mathematik der TU Hamburg zu begrüßen. Heute habe ich die Freude, dass wir eine Antrittsvorlesung von unserem neuen Kollegen Christian Dietrich haben. Und im Anschluss daran, so Pi mal Daumen gegen 2:15, wird Olaf Spinczig einen Forschungsvortrag mit Themen zu seinem DFG-Schwerpunktprogramm uns geben. Kurz ein paar einführende Worte zu Chris Dietrich. Chris hat in 2009 bis 2014 in Erlangen Informatik studiert. Ich freue mich total, dass so viele von Ihnen da draußen aus Erlangen zugeschaltet sind. Herzlich willkommen an alle. Nach seinem Studium hat er in Erlangen bei Daniel Lohmann auch angefangen zu promovieren und ist mit seinem Doktorvater dann an den neuen Standort nach Hannover gewechselt. Nicht Hamburg, nein, das kam einen Schritt später. Also erst Hannover, genau, und hat da erfolgreich 2019 seine Promotion abgeschlossen. Es kam eine kurze Postdoc-Phase von 2019 bis 2020 dort. Und im Jahr 2021 freue ich mich total, dass wir an der TU Hamburg so erfolgreich waren und Chris halt für unsere Junior-Professur zu Operating Systems gewinnen konnten. Ja, Chris, ich bin gespannt auf deine Antrittsvorlesung heute, die den Titel trägt New Directions for Managing Memory. Bitte sehr.
Ja. Yeah, so thank you very much for the introduction. As we've already heard, my talk today for my inaugural lecture will be new directions for managing memory. And I want to start with a very interesting piece of hardware that you see here, which is the drum memory of the TUHH Z23. It's a very ancient machine. It's from the 1960s. And drum memory is a big rotating cylinder with a magnetic surface, and because it has a magnetic surface, it is a persistent memory. And the interesting part about this memory is that it's very central to that machine. On the one hand, the rotation of the cylinder is the clock generator for the whole machine. So really the whole machine is clocked by the rotation of this drum memory. And on the other hand, this is also kind of the main memory of that machine. So you can really address individual bytes of memory on that machine from your instructions. So it has about 8,000 words of 40-bit memories, and you can read a lot of them. So what we see here is the centerpiece of a computer that is a persistent main memory. And from this starting point in our development, we really divide it into two directions. On the one hand, we are now having latency critical DRAM that is very, very fast, but that is not that big. So we can access DRAM really fast, and we also have random access. So it doesn't matter where you really read memory from DRAM, it's about always the same speed. On the other hand, we have the persistent part. We have hard disk. We had rotating disks in the past. Nowadays, we also have solid state disks, and there we have different characteristics. We have persistency, but we also have to read whole blocks of memory of data from those hard disks. And random read was traditionally very, very slow. However, in the recent years, we had hardware developments where kind of these two directions of development came closer to each other than ever before again. On the one hand, we have something called non-volatile RAM. So for example, Intel Optane. Those are modules that you can plug into your memory slots of your computer. It's byte addressable like DRAM, and it's a little bit slower than the usual DRAM, but it provides you with much more memory than you have with usual DRAM. On the other hand, we nowadays have SSD drives that are really big. So 30 terabytes storage, still block-oriented storage. And the interesting part is it has a high sequential read rate of about 8 gigabytes. But the interesting thing is random read is not that slow. So we get 6 gigabytes of random access, block-oriented random access, but random access over the whole surface of the disk. And the question is, how do we present these new directions in memory development to the user? And the classical answer that we would have from an operating system point of view, we put on our memory-centric glasses and say, oh, the solution probably is virtual memory. In the past, virtual memory was really successful in bridging the gap between disks and DRAM. So when we wanted to access the data on the disk, what have we done? We go to the operating system, we say, please, operating system, bring in the memory via system call. Then the operating system forwards the request to the disk, and the disk writes the data to the main memory, usually via DMA. And then the operating system configures the memory management unit to present this physical memory where the data is now located to the user in the virtual memory surface. And really, when you think about it, virtual memory is kind of the invisible operating system interface. Usually we say system calls are the operating system interface, but virtual memory is also some kind how to interact with the operating system. When it's set up, it's very efficient. So we only have TLB misses to get the translation from virtual to physical memory. On the other hand, it's really flexible. You can display any part of the physical memory within your virtual memory space. So arbitrary mappings are possible. And it is very established. So it is so to the core of our abstractions that we sometimes tell students, yeah, when you want to have a process is a virtual address space plus some activity, some thread living in that virtual address space. So it's very central to our understanding of what a computer program has as an execution environment. But when our now converging memory developments, we have several research questions that we can pose. On the one hand is the virtual memory management that we have done until now. Perhaps is the way how we do this. Is this a breaking block for the speed of those devices? We've seen those solid state disks are really, really fast. We have now DRAM and NVRAM. Perhaps we need some kind of unified abstraction between both kinds of memory. And when we have virtual memory in place, why not use it for more? How can we further exploit the flexibility of virtual memory? So today in my talk, I want to present you past, present, and future projects that we are currently working on. I will present you XMAP, how we can speed up file mappings within our virtual memory. I will show you our idea of the unified virtual memory abstraction model, and I will show you how we can reduce the attack surface of a program by exploiting virtual memory techniques. But let's start with XMAP, the fast and explicit file map. So when you want to access the contents of a file, you have two different routes that you can go. On the one hand, you can invoke explicit system calls like read and write and instruct the operating system to get a copy of the data within your memory into a fixed buffer. This is the explicit variant of doing I/O. You explicitly ask for the memory. The other variant is that you do file mapped I/O by invoking mmap, and by that you say to the operating system, please operating system, the contents of that file, make those contents visible within our virtual memory surface here. And by that we establish a one-to-one mapping between the virtual memory surface and some blocks on the SSD or within the file. And then when you access some part of the virtual memory surface where the data is not yet loaded, the operating system will bring in the data into a physical memory page and present it to you. So we have an automatic and lazy loading of data from the background storage. And even more, with file mappings, you can have an automatic write back to the disk so that you manipulate the memory and the operating system will flush out the dirty memory at some point in time. And this is really nice. It has some good properties that you can use. So it's transparent. A file mapping is transparent for the user. The program can really use pointers to point inside this file mapping. You can even put pointers in there. Not always a good idea, but you can do it. You can directly invoke your Q-sort algorithms on the content of the file. This is possible because it's really only memory. However, file mappings are some kind of a double-edged sword for some users. For example, for databases, you have the problem. Yeah, I said the operating system synchronizes back the data at some point in time. So you don't have any control about page evictions. This is really hard when you want to have some kind of higher level persistency guarantees. In that case, what you really would want from the operating system is more control about this page eviction decisions. And the other question that I ask is this mapping, this bringing in of memory and this evicting of memory, is this already fast enough? This is always a question in system software, but we will see in a moment that this is really a problem. So probably we want to reduce overheads. And yeah, so we did a little bit of an experiment, and we have some kind of mapping in our virtual memory, and without doing any input-output with the disk, are we able to install and remove physical pages from the virtual memory surface fast enough to even match the speed of our devices? And for that, so our task is install 4K pages and remove them again as fast as possible. And for reference, we put in here this black bar, and this black bar is 1.5 million IO operations per second. This is the amount of requests that such an SSD, such an Samsung PM7033 can really service in a single second. So 1.5 million operations. This is the benchmark. The first idea is to use the usual mmap. This is the blue line down here. And there we see this really doesn't scale with threads. Problem is it's lock contention at a single lock. This is really sequentialized. So perhaps not the best. Okay, next thing, we still use the current state of the art of Linux, and we use a large mapping, and we remove memory by doing some hinting to the operating system. And what we see, yeah, we nearly reach the 1.5 million IO operations per second, but this is really not good. So looking a little bit more into this, what we see is for every operation that we do, for every eviction of a page, what we really get is that we have to do a lot of TLB shootdowns. TLB shootdowns is that the operating system has to actively manage the caches within our MMU. So for every eviction, we send a lot of interprocessor interrupts, and we really can see that here for 40 threads. When you evict a single page, you have to send 39 TLB shootdowns for one operation. So basic idea, first fix that we apply. What we want to do is we want to batch our TLB shootdowns. We not evict one page at a time, but we always evict 512 pages. And in that case, we are up at this red line. So this looks really, really better. This scales better, not really linearly. So perhaps there are a few more bottlenecks that we can fix. However, we surpassed this 1.5 million operations per second really fast. So this is good enough. This is good enough to provide memory in the virtual memory space on the virtual memory surface fast enough to have this random access in a file mapping scenario. I said one SSD, but really you can have multiple of those. There's no problem in installing 10 of those SSDs within your server. And then you're not at 1.5 million operations, but you have to service 15 million operations per second. And really, we can't saturate that with our fixed variant of Linux. So perhaps we need a better abstraction. And the abstraction that we came up with is XMAP. XMAP is and utility to allow you to have fast and explicit file mappings. So what we still use from file mappings is that we have some area in the virtual memory that has a one-to-one mapping with the underlying block storage. So it really gives you this illusion that the content of your backing storage is in a one-to-one mapping in your virtual memory surface. However, we avoid this implicit bringing in of data and bringing it out again. So what we do is we provide explicit alloc and free and read system calls that we allow to be batched with 512 operations, and we don't have any implicit write backs. So this is good for users that know when to write back data onto the backing store. We use a few techniques. So we have a pre-allocated memory pool to avoid contention in the allocator. We use multiple free lists here, that we have different free lists at interface 1 and 2, and every thread decides from which interface it takes the memory. And we use lock-free algorithms to manipulate the configuration of the MMU. So when we use this abstraction, this XMAP abstraction, what do we get when we perform the same benchmark? So we again ask, how fast can we install and remove 4K pages from our virtual memory surface? And in this graph, I show you two different lines for reference. The one is the red line down here. This is the best line from the previous slide. So these are the 5 million IO operations that we had with the fixed version of Linux. And I have here the black line, and the black line up here, this is the raw memory speed that your DRAM can provide you. So on this experiment machine, the DRAM really gives you sequential read of 144 gigabytes per second. So when the operating system can provide 4K pages faster than this threshold, probably we don't have a bottleneck in our operating system anymore. So we have here 3 different lines for our XMAP. I said we have this stealing of memory between interfaces. So these are 3 different scenarios with no stealing, with some stealing, and with a lot of stealing of memory between interfaces. So the green line really is the worst case for our current implementation of XMAP. And what we see is when no stealing occurs, we reach over 300 million allocations per second. And this is equivalent to providing memory at the speed of 1,200 gigabytes of memory per second, if you would be able to read it. However, you are not able to read that in that time. So really, when you don't have stealing when your application is aware of these interfaces, you really don't have a problem with memory management anymore. So we are faster than raw memory, and we even faster than raw memory when the application structure is structured that it really works against our idea of having multiple interfaces. So even in the worst case, with around 50 threads, we saturate the memory. So from that, we learned that our new XMAP abstraction, which has a different semantic than the current file mapping. So we don't have implicit write back, we don't have implicit bringing in of data. It's different than the current Linux variant. So it's not a drop-in replacement, but it's much, much faster, and it provides this explicitness for something like a database. So we can now provide memory at a really high speed. But I want to come to another project that we are currently working on. So this is more of a concept, so I can't show you any numbers at this point. But our idea is to unify the different kinds of memory. On the one hand, the volatile memory that we had for forever, and the new non-volatile memory, and to bring this to the user, to present memory to the user. So first, I want to discuss with you what is the current abstraction in our operating system to provide persistency. And really, the abstraction for persistency is the file. The file is the persistent abstraction within our operating system. And a file consists of two components. A file brings together two components. On the one hand, a file has a name. So we really have objects within our operating system, and there is a name for that object, a human readable name. And with that name, we can find the object again. So within our operating system, there's some kind of index structure that maps like the file name /a/z to an identifier of the object. And the object, we call them inodes in operating system terms, is then the actual holder of this persistent memory. On the other hand, a file gives you virtualization. So a file is in its essence a byte stream. It starts with a certain offset, 0, and it has a certain extent. And you can say, oh, please give me the byte at offset 300. And the user doesn't have to know where that byte is stored. The file system virtualizes the in-file address to an actual block on the disk. So what the file system does, it resolves first the file into the inode, and then it translates you on its virtualization level, the file offset to the disk offset. And the last one, this is really close to what virtual memories also do. When you now in this classical view want to access some data, what you do is you ask the operating system, please bring in the data. Then the operating system traverses the file system, asks its caches, goes to the driver goes to the disk, and the disk then loads the data from its persistent storage into the DRAM, because there is a gap between the disk and the DRAM. We already talked about it. Then the operating system updates the NVMe configuration and presents this physical data to you. And then you can access the data. So this is the hot part for bringing in memory, bringing in data to the user. And now we have NVRAM. And with NVRAM, one line in this hot path really goes away. We don't have to load data from the persistent storage into the volatile storage anymore, because the CPU can directly access the non-volatile memory. But from that, you could really ask the question, do we still need those other parts of our hot path? Do we really have to ask file system, do we want to update the NVMe configuration anymore when we want to access file contents? So can we perhaps avoid that? So our idea, our new approach is, we have up here in our picture the page table tree of the NVMe configuration. So this is the configuration data for the NVMe, and this is shaped like a tree, and every subtree describes the virtual memory in some area on the power of 2. And our idea is we take a part of this tree and say, this is our new persistency abstraction, a subtree of the page table tree. And by that, we can unify volatile and non-volatile objects in memory. So we use the page table subtrees. And what we also do is we say, okay, naming is optional. You can do naming, but you don't have to. When you know the number, just use it. And what we do is that we don't do caching in DRAM. Not always. We allow you to do that as an optional feature, but we want to avoid. So the name for our new abstraction is the morsel. And the morsel is this subtree of the page table tree, but what you can really think of the morsel is that it's a sparsely populated huge page. Since it's a subtree of the page table tree, it has a rather coarse granularity. You can have 1 GB morsels or 512 GB morsels. This is the surface of the morsel in the virtual address space. However, you don't have to populate all of that surface with memory. You really can have gaps in that surface. And what we want to do is we want this morsel to be explicitly managed, like we have seen in the XMAP example. And now you have morsels that can either reside in RAM, where not only the user data up here, the blue boxes are in DRAM, but also the metadata, the page table configuration. On the other hand, we can also have persistent morsels that are now living in our NVRAM. And there, not only the user data is in persistent storage, but also the page table pages. And since our MMU, like our CPU, can directly address those pages, we can simply install a morsel within the virtual address space by just manipulating here a page table entry of 8 bytes and point that to the entry of our morsel. And thereby, our morsel 7 becomes visible in the virtual address space of our user, and he can directly access the memory. So this is the basic idea of morsels. And all the other features, we want to do them optionally. For example, what you can do now that you are able to bring in a morsel within your virtual address space, you can do the naming of morsels by yourself. You have now a piece of memory that becomes visible, and you can just use standard indexing tools like a standard map and put that into the surface of a morsel and translate from some symbolic names to the ID of the morsel, to the inode number as you will. But we cannot only do hierarchical file systems by that, but we could also just put the morsel numbers within your SQLite database, and then you have an SQL structured file system. So this is also an idea that we want to do. We want optional features like that a morsel has the constraint that it always has to be put at the same address within virtual address spaces. And by that, you can keep all the pointers stable within the surface of the virtual memory. And we want to have cached twins of morsels in DRAM because after all, NVRAM still is a little bit slow. So all of that is part of the PAPA-OS project, which is currently a proposal for the SPP 2377. And this is a collaboration with the University of Hanover. And another project that we have done together with the University of Hanover is our MMU project. And in our MMU project, what we want to do is to reduce the attack surface of a running application in a threat-specific manner. So first, I want to get into the problem. So what is the problem with the attack surface? So when you have a security issue, it consists usually of two parts. On the one hand, you have a vulnerability that some attacker from the outside can manipulate some aspect of the behavior of your running program. So this is most of the time not good, but it really becomes a problem when there is some possibility to exploit, to build an exploit around that vulnerability. And one technique to exploit existing vulnerabilities is rob chains. So in rob chains, what you do is you rely on code in the virtual address space that is part of your application, and you reuse that code to build some kind of a weird machine to execute your desired behavior. And for that, you use small parts of the code of the application, and these small code snippets are called gadgets. So the more gadgets you have within your virtual address space, the easier it gets to exploit a vulnerability. So in essence, more code means more gadgets are existing, exploits can use more gadgets, and it becomes easier. So in our small example here, what we have the main executable within our process with two libraries. And all of those executable files have some number of rob gadgets. This is just an example at this point. And when we sum it up, we have some kind of an effective attack surface of 100. So now that every threat has some chance to have some vulnerability, really the problem becomes more severe when you have multiple threads running in the same virtual memory. And just to get you an idea of what this might mean, now you have two threads and you have a higher probability when they are doing different jobs that there is a vulnerability that somebody could use. So just as an idea what the problem is, we could then say, oh yeah, there is an effective attack surface of now 200 because there are two threads with a certain probability being attacked from the outside, and then the attacker can use either on the one thread or on the other thread those 100 gadgets. However, in actually existing programs, threads have specific roles. They have either workload-specific roles or requirements of code, or they have row-specific requirements. For example, your garbage collecting thread doesn't need your encryption library. So perhaps the garbage collection thread shouldn't be able to execute the SSL library. So it would be nice to make that SSL library invisible for this one thread. So the core idea that we want to do is with our NMUs that we put on every thread a pair of glasses that the thread only sees those parts of the virtual memory that are important for him. And thereby we restrict the effective attack surface. So we start out in a running process that has a certain address space, and there we have the loaded code, we have the data, and we have the stack. And our idea is that we have multiple views on that virtual memory surface. We start out with view 0, and we have then a system call to create a second view on the same virtual memory. And both views are, when we start out, they are synchronized. They share the same data. So when you manipulate data in the one thread, it becomes also visible in the other thread. We do that by just simply having shared mappings between both address space views. So the physical memory is shared. And we allow then to make parts of a view private. We pin it. We allow the user to say, okay, here in this area of the address space, every modification should be private to this view. And therefore, each view has, for example, in the code segment, a private modifiable copy of its code. And then we can go on and we can purge parts of the executable code. We can remove the libSSL from the one view, and we remove the libJPEG from the other view. And by that, we really have two views with different number of gadgets. And in each view, we can have multiple threads running, like in a usual address space. But we can migrate threads between views within the same process. So they have actually the same virtual memory, but they have different glasses on. They don't see everything the same. Most parts of the virtual memory are the same, but in some tiny details, it's different. And as we still have this shared mapping of the data, they can effectively communicate to each other. All pointers remain visible, remain stable. So we really don't have any translation overhead between the different views. And we see here in the one view, 68 gadgets, and there 55 gadgets. And we applied this technique to MariaDB. And what we've done, we took MariaDB and we put each worker thread into its own memory management view. And we not only removed individual libraries from the virtual memory surface, but we wiped out individual functions from our libraries. Actually, we started out with empty memory management views and then loaded lazily functions back into them. And we did some control flow integrity check. And by that, what we get is now that we have for each thread the possibility to have a private view on the code, what we really can do is deep loading, dynamic deep loading of the whole process. So traditional deep loading techniques, existing deep loading techniques, they most of the time, they focus on the libraries because they say every function within the main executable, it wouldn't be in the main executable if you wouldn't use it. So it's not possible to purge usually functions from the main executable. However, with our technique, as we make the scope of the deep loading smaller down to individual threads, we can say within an NMU, there's only the code that this specific thread really needs for its duty. When you have a thread that services only read-only workloads, like we've done here, we see that a different set of functions is used than when you have a client that has a write-only workload or a client that has an insert workload. So there is some common core of functions in MariaDB that is used by all kinds of workloads, but really they are different. So we have thread-specific, workload-specific deep loading. And what we also see, this is really effective. So overall, we can remove the number of executable bytes within our running process by up to 90%, 93%. So this really makes a difference for the attackability. So I want to come to a conclusion in my talk. First, what have I told you today? I've shown you XMAP, fast and explicit file mappings. What we get by that is 58 times faster 4K allocations within our virtual memory space. I've presented you morsels, which are in unified abstraction, and thereby we get a zero copy access path to our non-volatile memory. And I've shown you MMUs. How can we reduce the attack surface in a thread-specific or context-specific way? And by that, we reduced the attack surface by 90% for MariaDB. And I hope I could convince you that virtual memory is really the invisible operating system interface and that there is a lot to do in the future. So thank you very much. And yeah, I'm now happy to take all your questions.
Ja, herzlichen Dank, Chris, für diesen Vortrag. Es war total spannend zu sehen, was man da auf dieser Abstraktionsebene in den Eingeweiden des Betriebssystems so alles irgendwie tun kann. Ja? Fand ich extrem spannend. Ich habe im Chat gesehen, dass Olaf dort eine Frage gepostet hat. Olaf, schieß doch bitte direkt los. Und für Folgefragen heben Sie doch in Zoom gerne einfach von jetzt an die Hand und dann sehe ich ja direkt, wer noch etwas auf dem Herzen hat.
Okay, ja, gerne. Ja, die Frage, die mir in den Sinn kam, als du XMAP vorgestellt hast, war, also man kann natürlich allerlei verschiedene Abstraktionen in die existierenden Betriebssysteme einbauen, die alle dann halt in dem jeweiligen Anwendungsfall besonders effizient sind. Ja, das klappt ja in deinem Fall da super gut. Ich habe mich nur gefragt, gibt es da irgendwie auch eine gemeinsame, idealerweise minimale Basis? Konkreter, kann man dann auch die Standard-MMAP-Schnittstelle eventuell aufsetzen auf deiner XMAP-Abstraktion?
Was ja fehlen würde, um so eine ganz klassische MMAP-Abstraktion zu haben, ist dieses implizite Reinbringen von Speicher und Rausbringen von Speicher. Das Dahinmappen von Speicher, das sollte relativ leicht zu bekommen sein, indem man eben den Page-Fault-Fall passend behandelt. Das Problem, was man dann ein bisschen hat, ist, man kriegt dann immer nur eine Seite at a time an Informationen von der Anwendung. Was wir hier auch gesehen haben, ist der Effekt von Batching. Beim Allokieren von Speicher konnten wir halt immer sehr viele Seiten auf einmal reinbekommen, haben nur einen System Call dafür und haben deswegen den Overhead allgemein niedrig gehalten. Beim Entfernen von Speicher ist es so, naja, da wollen wir ja auch, dass wir das Entfernen von Speicher, da müssen wir irgendwie rausfinden, dass die Anwendung das wirklich nicht mehr braucht. Und der Vorteil, den wir durch dieses Explizite haben, ist, dass zum einen die Anwendung sich darauf verlassen kann. Ich meine, natürlich könnten wir Seiten einfach aus dem XMAP-Surface wieder rausreißen, aber welche Garantien würden wir noch geben? Was wir momentan haben bei den XMAP, wenn du ein Stück Speicher irgendwo hingemappt hast, dann ist es da, dann geht es nicht weg. Wir machen Swapping aus, der Speicher verschwindet nicht. Wir haben wirklich, die Latenzen sind dann auch vorhersagbar für dieses Stück Speicher. Also man bekommt auch eine ganze Menge davon. So, klar, man kann all dieses Implizite in MMAPs wieder reinbauen, aber was wir auch gesehen haben in unseren Experimenten ist, das kostet richtig. Also gerade in dem Fall, wo wir ganz, ganz viele Threads haben, ganz viele Cores, die auf diesem Mapping rumarbeiten wollen, dass das wirklich teuer ist. Also ich weiß gar nicht, ob diese implizite, dieses Entfernen von Speicher durch implizites wieder entfernen, ob das wirklich worth the effort ist. Ja, und ob in dem Fall es überhaupt nötig ist, dass wir das brauchen.
Es erinnert mich auch so ein bisschen an halt dieses alte User-Level-Paging-Konzept vom Mach-Betriebssystem. Hätte man damit auch sowas umsetzen können vielleicht? Also wäre das vielleicht eine Abstraktion, die Linux irgendwie doch auch wieder bräuchte?
Ja, also es gibt in Linux diesen User-Fault-D. Damit kann man, glaube ich, genau sowas nachbauen. Die Overheads sind dann allerdings, glaube ich, sehr schwer in den Griff zu bekommen. Was wir hier halt machen können, dadurch, dass wir eben nicht einfach den Page-Tree so, wie er ist, als Abstraktion rausgeben, sondern so ein bisschen Zucker drüber machen, dass wir sagen, es gibt dieses Stück VM-Surface und du kannst es manipulieren und wie die Page-Tables aussehen, das vergisst du am besten. Dadurch können wir halt sowas wie wie logfreie Algorithmen auf dem Page-Tree direkt verwenden als Betriebssystem, ja, indem wir die Kontrolle darüber behalten. Und diesen Grad an Geschwindigkeit rauszubekommen, indem er ständig in den User-Space wechselt, da weiß ich nicht, wie man das machen würde.
Ja, da bräuchte man so eine Stored Procedure irgendwie im Kernel, ne?
Ja.
Okay, ich frage nicht, ich finde es super interessant, könnte wahrscheinlich auch noch länger mit dir drüber reden, aber ich denke, die anderen wollen auch mal was sagen.
Ja, gibt es noch weitere Fragen aus dem Kreis der Teilnehmerinnen und Teilnehmer hier? Bitte gerne die Hand heben. Tatsächlich was, aber das war keine Frage. Okay. Mich würde eine Sache interessieren. Durch deinen gesamten Vortrag hinweg zog sich als Gütekriterium im Prinzip Performance. Ja? Wie viele Speicherzugriffe oder wie viele Speicherkapazitäten pro Zeiteinheit kriegst du irgendwie adressiert und dergleichen. Wie sieht das denn aus, wenn man andere Kriterien anlegen würde, wie beispielsweise in einem mobilen Gerät Energieeffizienz oder dergleichen? Ist es da wirklich eine gute Idee, direkt auf dem großen Massenspeicher herumzuoperieren, oder sollte man da aus Energieeffizienzgründen nicht vielleicht doch den Content erst in einen flüchtigen Speicher kopieren, dann super energieeffizient darauf arbeiten? Was meinst du?
Das ist tatsächlich eine spannende Frage. Das kommt aber, glaube ich, auf die jeweilige Technologie an, wie da eben die Energieverbräuche tatsächlich aussehen. Deswegen haben wir auch noch für die Morsets zumindest die Idee, dass wir also explizit erzeugte Schattenkopien von echten Morsets nehmen, die man dann als Ganzes also die man auch lazy in den DRAM laden kann und wieder zurückbringen kann. Und immer mit dieser Idee, dass man das explizit macht, dass das Betriebssystem nicht versucht, zu magisch zu sein in seinem Management von Daten. Also dass man Mechanismen bereitstellt in der Anwendung eher die Entscheidung über die Policy in die Hand. Und auf manchen Geräten wird es so sein, dass der DRAM weniger Energie braucht als der nicht richtige Speicher.
Ja. Sorry, jetzt nutze ich gerade die Zeit, die ich hier. Das öffnet nämlich genau die Tür zu meiner letzten Frage, die ich mir hier auf meinem Spickzettel notiert hatte. Das explizite Management, jetzt in dem Fall mit den verschiedenen Views und den Maps, die du zum Schluss vorgestellt hattest, das ist ja, wenn ich dich richtig verstanden habe, eine Sache, die der Software-Developer irgendwie spezifizieren muss. Und wenn ich jetzt ein super komplexes Softwareprojekt irgendwie habe und ich sehe mich mit der Aufgabe konfrontiert, deinem Betriebssystem zu sagen, so, das ist die Brille Nummer 1, das ist Brille Nummer 2 und Brille Nummer 325. Wie schätzt du das denn? Ist das praktikabel?
Also für diese Attack Surface Reduction haben wir das alles ziemlich durchautomatisiert. Also was wir eben machen ist, also wir mussten MariaDB, ich glaube, so 50 oder 100 Zeilen hinzufügen, damit wir wissen, an welchen Stellen wir in die anderen Views wechseln. Das kann nur die Anwendung wissen, wo dieser Übergang stattfinden kann. Und wir haben dann die Information darüber, wo eine Funktion liegt, eben aus den Binär-Metadaten, aus den 11 Metadaten rausbekommen. Und dann immer, wenn eine Funktion wirklich am Anfang angesprungen wird, dann laden wir sie in diesen View. Wir checken vorher noch, dass dieser Aufruf wirklich valide sein kann, also dass nicht einfach irgendjemand durch seinen Exploit-Code diese Funktion in den NVMe geladen haben will. Und dann machen wir das. Dann laden wir diese Funktion wieder zurück in den Speicher und damit kommt sie ausführbar und wird sie ausführbar.
Okay.
Also man muss dafür nicht viel an an der Anwendung ändern. Das liegt auch daran, weil diese verschiedenen Views, die schauen auf den gleichen virtuellen Speicher. Es ist nicht so, dass die nebeneinander sind, dass die Adressen sich unterscheiden, sondern das ist der gleiche virtuelle Speicher, nur mit einer anderen Sicht darauf. Die bleiben auch immer synchronisiert. Wenn ich hier ein mmap an eine Stelle mache, dann ist das in dem anderen auch sichtbar. Ja, das ist anders, als wenn man jetzt versucht, mehrere Prozesse zu starten und sagt, darüber machen wir die Isolation zwischen unseren einzelnen Workloads, weil da muss man die Anwendungsstruktur tatsächlich größer ändern. Was wir schaffen, ist weiterhin diese Vorteile von Multithreading. Wir leben im Grunde alle in der gleichen Welt. Das ist nur so ein bisschen anders.
Ja, okay. Sehr interessant. Nochmal, gibt es noch weitere Fragen von Ihrer Seite? Nein, offenbar nicht. Dann bleibt mir für den Moment, Chris, dir ganz herzlichen Dank zu sagen für diese spannende Antrittsvorlesung. Toll, dass du zu uns an die TU Hamburg gestoßen bist und alles Gute für deine weiteren Forschungen hier zu Betriebssystemen.